Welcome to AV Brief's essential lesson. This lesson is on climbing and descending. It's assumed that you have already studied the previous lessons. There is technical knowledge in here that is going to be carrying on from these previous lessons. As always, let's get started with some revision and make sure you are ready for this lesson. Number 1. Name the two types of drag that make up total drag. Number 2. State why drag is higher at slow airspeeds than at medium airspeeds. Number 3. State the sequence used to put an airplane into straight and level flight. Number 4. What is the purpose of dihedral? Very well done on getting this far. Let's keep moving forward, but if you can't answer those questions, go back and review the previous lessons. In this briefing, we'll be looking at climb theory, descent theory, as well, how to climb and descend. We'll start by looking at the climbing part of climbing and descending. The definition of climbing is to gain height at a steady, specified speed, while maintaining a constant heading. This is a big lesson and some of the theory can get in depth. So grab a beverage, and a good chair, and let's get started. By the end of this lesson you will be able to, with the aid of a diagram, explain why thrust has to be increased to climb an airplane. Define best angle of climb and best rate of climb. State, in the correct order, the sequences of actions required to enter and maintain a steady straight climb, and level off at a nominated altitude. Describe the use of rudder and specify instrument indications during a climb. Describe pilot actions required, if the engine is overheating during a climb. The forces in a climb. From the previous lessons, you'll remember that there are 4 forces in action in flight. Those same forces are in action in a climb. A vector. This is a quantity which has both direction and magnitude. That is to say, it has direction and strength. A resultant vector. This is a single vector which is the sum of 2 or more vectors. The example here shows the green lift and blue thrust. Together they form a single vector which is shown in orange. This can be called the thrust-lift vector. It is the combining forces of lift and thrust, resulting in a force up and forward. There is also the weight-drag vector. This is the combining forces of weight and drag. These result in a force down and backward or rearward. When we put an airplane into a climb, most of the forces are following the same pattern. Thrust acts in line with the power plant or propeller. Drag acts rearward against the direction of travel. And lift acts perpendicular to the direction of travel. But weight will always act towards the earth, as it follows the law of gravity exclusively. We still have vectors when we are climbing. They help to visualize what's happening to our forces. You can see that the first change is with the drag, weight vector. Notice that the drag is still in line and opposite to the direction of travel. This has the effect of pointing drag towards the ground. As it is acting towards the ground, it is adding to the weight of the airplane. This weight increase now makes it harder for us to climb, as the airplane weighs more. Look what happens now to the thrust-lift vector. The lift is tilted rearward. Just like in the induced drag scenario, we saw the lift tilt rearward and create induced drag. This has the same effect, but it also reduces the lift available for staying level, let alone making the airplane climb. In order to start to climb, there will need to be an increase in one or more of the forces in action. There's not much we can do to increase lift, once we have set an attitude. So therefore, the only thing we can do is to increase thrust. Increasing thrust will increase our thrust-lift vector, enough so that it will balance out the drag-weight vector. Taking a deeper look into climbing, we learn that there are several different types of climb we can use. The first one we will look at is called the best angle of climb. It is referred to as Vx. It is the climb performance that results in the greatest height, in the minimum horizontal distance. All of our speeds in flying are appended with V. V1. V2. Vx. The V comes from the French word vitesse, which means speed. So our best angle of climb, or Vx, results in the highest climb while traveling not too far forward. This could be useful when climbing over an obstacle such as a hill or a fence at takeoff. The Vx speed is determined by where the maximum excess thrust is available. The thrust available is dependent on the horsepower available in the propeller. In this diagram, we can see the thrust required curve. Remember this one? It comes from the total drag curve. So the drag curve gives the thrust required for level flight. Now we add the thrust available. This is derived from the engine and propeller and comes from a word which means the act of pressing. So it's how much air the engine and propeller are pressing out behind them. In between these two curves is where level flight is possible. To find our Vx speed, we take the point where there is the maximum excess thrust available. That is our Vx, or our best angle of climb speed. This speed is always found in your pilot's operating handbook, or UPOH. The next type of climb we will look at is called the best rate of climb, or Vy. This climb gives the climb performance that results in the greatest height in the minimum time. So Vx gives the best climb in the least forward distance. And Vy gives the best climb in the minimum time. Vy is a more common climb. It is quicker over the ground, so you get to your destination sooner. It is also a faster speed. So it will be better for cooling the engine. Vx was derived by finding the speed where the maximum excess thrust is available. Vy is found by this equation. If you look up the definition for power, and you should look up in a dictionary, and understand all of the words we are using in aviation, you will see that it is equal to force times the distance. That means that the power something is outputting is equal to how much force it is exerting over a given distance. So a car's power is how much push, or force, it has, times the distance it pushes over. In an airplane, the force is actually the amount of thrust we have. We know that thrust is the pushing force. So we can replace force with thrust. And distance divided by time is equal to an airspeed. Airspeed is simply the amount of distance we travel in a given time. For example, 120 knots or airspeed means we travel 120 nautical miles per hour. That's all. Now that we know our power is just the thrust times airspeed, we can see something else. We can see that power available is the thrust available times the airspeed. And then the power required is the thrust required times the airspeed. So Vy is determined by where the maximum excess power is available. Vx, maximum thrust available. Vy, maximum power available. Just to add some more data to this graph. Thrust available started high and slowly went down. Thrust is at its maximum when the airplane is not moving. This is because the engine is at full output and the backwards pushing force is at its maximum. Once the airplane gets fast enough, the pushing force from the engine and propeller is not enough to push the airplane any faster. It's already pushing it through the air. And it's at maximum output, so it has no more thrust, or force, to give. Power, on the other hand, is force times airspeed. So at zero airspeed there is little power. This is on the left side of the graph. As airspeed increases, so does the power, until the point when it is unable to produce as much force for the higher airspeed. That's where the red line starts to drop. So the three different types of climb we have available are summarized here for us. Vx is the maximum height gained in the least forward motion, or distance traveled. Vy is the maximum height gained in the least amount of time. And then cruise climb. Cruise climb sacrifices some climb performance for a greater ground speed. So if you need to get to where you're going as fast as possible, and let's face it, most flights do want that, then you would use a cruise climb. There are factors which affect climb performance. Depending on how much they vary, this can have a major impact on climb performance. Altitude and temperature. As altitude and temperature decreases, air density decreases, resulting in a reduction in the power available, and a higher speed required to produce lift. When we take the same power graph to determine our Vy power, we can show the effects of that reduction in power. With the power reduced, and the power required increased, the result is that level flight is available throughout a smaller area. Now there is less power available and more power required. Weight and flap. The increase in drag caused by the addition of flaps increases the thrust required. This can be seen back in our forces in a climb section. Additional thrust is required for a climb. So adding more drag will result in more thrust being required. Another thing that affects our climb performance will be a headwind. Now is a good time to define what we mean by climb performance. Our performance in a climb can mean what we are trying to achieve. So in a best angle Vx climb, our performance will be the height gained in the least forward distance. In a Vy, best rate of climb, the performance is the height gained in the least time, or the amount of height gained in a given time. In this case, a headwind could increase our Vx performance, as we would be traveling slower over the ground. The last factor we're going to speak about is the slipstream effect. This is a climb produced yaw to the left. Right rudder is required to balance the climb. The addition of rudder adds some drag. This reduces the performance of the climb. Let's review climbing. Which of the four forces provides the significant force in a climb? Define best angle of climb. Which symbols relate to best angle and best rate of climb? I'll give you a hint, they start with V. Name two factors which affect climb performance. This is descending. Descending, or descent, is a condition of flight where the aircraft loses height by either gliding at a constant airspeed, or using controlled power to lose height. Let's introduce best glide speed. This is the speed at which an airplane will achieve the maximum gliding distance. Our outcomes for this lesson are: given an airplane operating handbook, reference the best glide speed for an airplane. Explain how flying faster or slower than best glide speed affects the glide path. Describe the pilot actions to enter and maintain a glide descent and a cruise descent, as well as how to recover to level attitude. Explain the actions to ensure that engine temperatures are maintained within limits in descent. There are forces working on a descent, the same way the forces are working in cruise and climb. But there are some changes. These forces must remain in equilibrium. During a descent, students are surprised to discover that lift and drag both resist the descent. This can be seen in the diagram. Lift is acting to hold the airplane upwards. The drag is now acting upwards also, resulting in two forces resisting the descent. the addition of thrust counteracts some drag, which results in a shallower descent angle. Let's use glide angle to further explain the descent, and how it could be shallow or steep. Glide ratio is the ratio of the forward distance traveled to the vertical distance when it is operating without power. This ratio shows how many units forward compared to how many units of descent, or put another way, lost height. In the diagram shown, the diagram on the left shows a typical training airplane glide ratio of 11:1. This means for every 1 unit of lost height, it will travel 11 units forward. You can replace the term units with feet, or meters, or millimeters. It doesn't matter what you replace it with. It just means the same thing. On the far side of the ratio, a glider, which is made for gliding, will have around a ratio of 20:1. That means for every 1 unit of lost height, it will travel forward 20 units. That's nearly twice as efficient as our training airplane. So the glide ratio is an important figure, as it tells us how far we will travel if we lose engine power. The lift-to-drag ratio determines the glide angle. So the only two things which can affect the glide angle are lift and drag. Once the best glide speed, or best glide angle are achieved, there is no way of increasing lift, or reducing drag. Any change from the best angle or speed is negative to performance. Remember, the angle of attack is what sets the best glide performance. But as it is expensive to have an angle of attack meter in light aircraft, the angle is converted into a speed. This is fairly accurate. Let's look further into the lift-to-drag ratio. The best lift-to-drag ratio is found where drag is least. Most light aircraft will have a glide ratio, which will be about 10:1. It is the pitch attitude, which gives us our best glide. The angle of attack. However, due to high cost, we use a speed to approximate this attitude. We can see here that the best glide range speed is also determined by a line tangential to the power required curve. A tangent is a straight line that touches a curved surface at a point, but does not cross it at that point. You can see the line is touching the underside of the power required curve on the lower graph. At that point where it touches, is the lift-to-drag maximum. Lift-to-drag maximum gives us both our minimum drag or best glide speed. And it also gives us the maximum range speed. So, in the upper graph you can see that at the point where drag is least, in the total drag curve, is where we get lift-to-drag max. That gives us minimum drag and maximum lift. In the lower graph, it is the same speed, but it is found by running a tangential line on the power required curve. Both the speeds are the same. Because it is the speed where lift is greatest in relation to the amount of drag, it will give you the furthest distance when gliding, and it will give you the best speed for minimum drag. That speed is used to get the maximum range out of the airplane. Because it will take you the longest distance on the fuel available. So, the best lift-to-drag ratio establishes without power, the best glide speed. With power, it establishes the maximum range. And, maximum range is the distance an aircraft can travel by flying at the most economical speed. The maximum endurance is determined by least power required. This is different to the range. Maximum endurance is the maximum time an aircraft can travel, or to say it another way, the maximum time it can stay in the air, by traveling at the most economical lift-to-drag ratio. So, maximum range travels the furthest distance. Maximum endurance stays in the air longest. You can see on the lower graph that to stay in the air the longest time will require less power and therefore less fuel being consumed. Hence, it can stay in the air for longer. To illustrate our discussion on glide distance, we have here a graphed glide distance. The green line, being best glide speed, is the best glide speed. Any change to that speed will result in less distance traveled over the ground. It doesn't matter if you increase or decrease the best glide speed. They will both result in traveling less distance over the ground. So any deviation from best glide speed results in a decreased glide angle. The explosion is just for effect. If you change your best glide speed, there may, or may not, be an explosion at the end. We'll look at factors which affect angle and rate of descent. These are very similar to the factors that affect the climb. Weight. With an increase in weight, the lift-to-drag ratio must stay the same. Increasing speed is the only way to increase lift. The added lift compensates for the increased weight. The wind. Wind will change just the angle of the descent. A headwind, from in front of you, will push you backwards, making you travel less distance over the ground. A tailwind, from behind you, will help you travel further over the ground. Altitude and temperature. At higher altitudes and temperatures, the air density is reduced. Less dense air contains less air particles, and so it gives less performance in creating lift. The lift-to-drag ratio decreases proportionally. So as they both reduce at the same rate, the actual ratio is unaffected. There is less air resistance. The TOS or true airspeed increases. This means you travel faster through the air. Your indicated airspeed stays the same. This is because you are passing through less dense air. So you will still travel at the same speed on the airspeed indicator, but you will be going through more air to get that speed. Power. Any small amount of power added will improve thrust. Power will counteract drag. It reduces the rate of descent. And it increases glide distance. Flap. Flap increases drag. The nose needs to be lowered to maintain the same airspeed. Flaps create a steeper approach. All this can be better for normal approach and landing configurations. For a glide descent, they will always reduce glide distance, if there is no added power. Okay, very well done to get this far. Let's now look at the actual procedure to set up an airplane in a climb. The two processes, climbing and descending, are very similar in the procedure. And to make it even easier, we are going to use the same 7-step process as straight and level. Let's assume we are flying straight and level. The first thing to do is to set the climb power. This will be different for many airplanes. Consult your company and airplane handbook. Let's say for this exercise it's 2400 RPM. Next, set the attitude. We would use a reference attitude out of the window in front to set this. Find out what it is from your instructor or by trial. But it will always be the same for that airplane. Once you have held that attitude for a few seconds, check the performance. The performance for a climb will be the airspeed and the altimeter or vertical speed indicator. It is a climb speed that we are trying to accomplish. And that speed is achieved by setting the right attitude. Now use the trim wheel to relieve the pressure off the yoke. Wait a few seconds, let the forces balance again, and trim again if required. Repeat this until you are holding the correct speed, and don't have to use much, or any force to maintain that attitude. Ensure the wings are level. Do this again, out of the front windscreen. Make sure the wings are level with the horizon. Double check with the attitude indicator, but it is not your primary reference for wings level. Check the balance ball is centered. This is to make sure you are holding in enough right rudder. Usually if you're not holding enough rudder, the heading will slowly drift off your intended heading. So that's a good check. Finally, make sure you are heading in the correct direction, and that you haven't drifted too far while setting up for the climb. If you have, make a small adjustment, or a big adjustment if you really went out. Then start to cycle through these actions. You get quicker with practice and can start to have attention on most of them at once eventually. Let's put all of what we've learned into practice now. To initiate a climb. Lookout. Power. Plus attitude. Equals performance. Stabilize, then trim. Check wings are level. Ball is centered. Heading in the right direction. Throughout the climb. Clear ahead, every 500 feet. Monitor your altitude and indicated airspeed. Ensure you are balanced with the rudder. Check heading. Monitor engine temperatures. The way to reduce an overheating engine is to simply lower the nose attitude slightly. This will increase the speed and get more air flowing through the engine. If that doesn't work well enough, you can also look at reducing the power. You would obviously need to lower the nose attitude more, to maintain your desired airspeed. Top of climb. There needs to be some anticipation of the upcoming top of your climb. Leveling off can take several seconds, and so good planning is essential. A good rule of thumb is to start the level off at 10% of your vertical climb speed. So if you are climbing at 500 feet per minute, you would start to lower the attitude, at 50 feet prior to your nominated altitude. Set level attitude. Observe speed increasing. Once at desired speed, or within 10%, reduce power to cruise power. Maintain attitude. Trim. Wings level. Ball centered. Heading in the right direction. Again, you will want to cycle through this a few times till the airplane is stabilized. The descent procedure is going to use the same process. We won't go through and explain it all again, but let's go through it in relation to the specifics of the descent. Set power for descent. Set attitude. Same as for climb, this should be a known attitude. Refer to your instructor, handbook or company procedures. Check performance after a few seconds. It's mainly the attitude that's the performance. But ensure airspeed isn't getting too high, and vertical speed is within the desired range. Usually it's from 500 feet per minute to 1000 feet per minute. Again, trim the airplane and keep the attitude stable. Check wings are level, the balance ball is centered and you're heading in the right direction. Good. Let's go through the full process for the descent. Top of descent. Lookout. Power, plus attitude. Equals performance. Hold, stabilize. Trim. Wings level. Balance ball centered. Heading in the right direction. Throughout the descent. Maintain lookout. Including below. Monitor vertical speed and indicated airspeed. Keep balanced. Heading is correct. Engine temperature should be within range. Believe it or not, engine cooling can be an issue in the descent. If the engine gets too cool, you can add some power or reduce the airspeed. Approaching target altitude, use the same 10% rule of thumb. Set cruise power. Set level attitude. Check level performance. It should be maintaining altitude. Trim. Wings level. Ball centered. Heading in the right direction. In summary, in this briefing we looked at forces in climbs and descents, types of climbs and descents, factors affecting climbing and descending, glide angle and ratio, application, how to climb and descend. You should now be able to, with the aid of a diagram, explain why thrust has to be increased to climb an airplane. Define best angle of climb and best rate of climb. State, in the correct order, the sequence of actions required to enter and maintain a steady straight climb, and level off at a nominated altitude. Describe the use of rudder and specify instrument indications during a climb. Describe pilot actions required, if the engine is overheating during a climb.